Adams from Michigan. He will tell us all about the future. It's not astrology, it's astronomy.
Oh, so thank you for having me here today. I should probably say a word or two about what I mean by history. When I'm talking about the future history, I do not mean the same thing that all of you real historians mean. So exactly what I'm going to do is the following. What I'm going to do is I'm going to assume that we actually know what the universe is like today and how we got from the Big Bang to the present. As Greg Bothan told us yesterday, that might be a dubious assumption, but nonetheless we'll go with it. I'm also going to assume that we know what the laws of physics are and that they won't change too much. And then I'm going to make the third assumption that I actually know what the heck I'm talking about and can do the calculations to start with those two assumptions and calculate forward to see what will happen in our universe. So I'm going to tell the story of our universe based on the basic premise of the expanding universe that this whole conference is about, and see what happens into the far future. We have this beautiful sports car that we built, so we're going to take it out and see how fast we can go. So, dangerous. So to orient you, I'm going to go through 5 different stages of the universe, and I will have to define a new time unit for you. So sometimes I'll use a logarithmic unit of time, where time is 10 to some power of years. The exponent will be the cosmological decade. Just to orient you, the universe is 13.7 billion years old now, which is about 10 billion years old. So we're in the 10th cosmological decade. We'll tell the history all the way up to 10 to the 100 years, or cosmological decade 100, and we only have 20 minutes, so where should go? So the first era is the era that takes us from the Big Bang until when the first stars form. I'm not going to talk about this. This era ends at the first generation of stars, which could be as early as when the universe is 1 million years old, perhaps as old as when it's 1 billion years old. That's exactly what Richard Ellis told us about, and what he will tell us in the next year, 2 years. He will tell us when that epoch changes. So when we leave the primordial era, we enter into the stelliferous era, when stars are generating most of the power. And that's the current era that we live in now. We're in fact, logarithmically speaking, right in the middle of this stelliferous era. So that takes us to the present, and we want to go from here upward. So the current data from the microwave background, supernova 1A data, and just measurements of dynamics of galaxies and galaxy clusters tell us that the matter content of the universe has some admixture of dark matter and some admixture of vacuum energy, and I'm going to assume that this is the right place to be, and I'm going to use this as the basis for seeing what happens next. So this is a movie of structure formation. I'm starting with a small a, and right now we're at the present epoch. And then I'm going to continue the movie, because I'm too lazy to turn my computer off, I'm going to continue it into the future. And you see that, like many movies, as we go towards the end, the plot gets disappointing. Because you see, from here on out, ain't nothing happening, right? This is a zoom in of the same kinds of filamentary structures that you saw in the previous 2 talks from the previous speakers. And what we, although this is zoomed in on the largest cluster in the universe. And what you see is that after the universe is about 5 or 10 times larger than today, there's very little that happens, okay? So if I look at stills from the movie, you see that at the current cosmic age of 14 million years old, we see this filamentary structure that you saw in actually better pictures in the earlier talks. But if I zoom in, you see that by the time the universe is about 92 billion years old, every bound structure in the universe today becomes its own island universe. And this is an island universe in a slightly different way than what we've been talking about, but it really does become an island universe, because at this time, there's nothing in this frame, but at about this time, or maybe shortly thereafter, you can't actually even see galaxies that are outside this little thing. So each bound structure, which means basically each cluster of galaxies, becomes its own little universe, its own little unit. And if you were an astronomer or a historian at that time in the future, all you would know about observationally would be what's in this little tiny dot. Now, one question that you might ask yourself or ask me is, why should we waste our time worrying about the future? And one thing is just because it's cool, but another is that it actually informs our understanding of the present day universe. So if you think about it, these filamentary structures that we've seen a couple of times now, in each of the 3 talks in fact, That means that if you ask what's a seemingly sensible question, namely, what's the mass of a galaxy? There's not an answer to it. And the reason why there's not an answer to it is you don't know where to draw the boundary, because there's these filaments that stretch on forever, right? So what cosmologists do today is we stand on our heads to define the mass of the galaxy. So there are five different probes or proxies for mass. One is something called mass M200, where you take all the mass that's within a radius, where everything in that radius has a density that's 200 times the background density. That's a bit of a mouthful, that's M200. Each one of these is changing. This is the mass proxy versus time. Each one of them changing at the present epoch. But as you go to the future, all of them become constant. And since each bound entity becomes its own little island in the future, there is in fact a well-defined mass. It turns out that the well-defined mass is 1.95 times M200. So we can actually define the masses today by taking the simulations into the future to see what will happen. You can also calculate the universal density structure of these halos. For those experts out there, presently everybody says that the present day halos have a universal form, which is the NFW form. In the future, the NFW form steepens to something more like a truncated Hernquist form, but it has this form with the truncation radius. Point being that galaxies and halos of galaxies, more precisely, or halos of clusters today, aren't really quite done forming. So you have to actually look into the future of the universe to actually answer the question, like, what is the mass of a galaxy? And that's one of the things that these studies bring. There will be more, but as you see, as I go through this talk, I'll have less and less time, so I'll have to be slightly faster. Now, the other point is that one of the reasons why we believe in Big Bang Theory today is that there are at least three main pillars of it. The first is the expansion of the universe, which of course all started 100 years ago on the mountain here, and that's what we've been talking about primarily in this conference. There's also the micro background and Big Bang nucleosynthesis. And jointly, these three successes of Big Bang Theory are the main reasons, I think, why we believe in it. Now, if you go to the future of the universe, like we just talked about, when each bound structure is its own little island, then we lose all three of these. See, the expansion of the universe can no longer be observed once everything is moved outside our local horizon and we can't look at redshifts anymore. The microwave background itself will be redshifted as the universe continues to expand exponentially. So once the redshift, right now the microwave background wavelength is about that big. So once that distance scale expands to be the size of a galaxy, it's going to be hard to build a radio telescope to see the microwave background. And then it gets exponentially worse from there. And finally, one of the reasons why Big Bang nucleosynthesis works is that the universe is young. Most of the helium in the universe today was produced in the Big Bang, not in stars. But if you wait long enough, the stellar content will grow and erase that. So this is a good time to be a cosmologist. 100 million years from now, you guys are out of business, right? Now,
in 100 billion years, today's astrophysical journal will be vital.
Yes, it will be very vital. So all you archivists out there,
we have to preserve it.
preserve it. So we can write down the future expansion of the universe in a single equation under the assumption that the dark energy is actually constant. And you get this form, and in the future, the scale factor of the universe expands exponentially with the constant, which gives us the opportunity to define a new constant. It's going to be this factor here times what we now call the Hubble constant. So this gives us an opportunity to define a Slipher constant. So now we're going to look at the content of the universe. Each bound structure, each halo, becomes its own island universe, and that's kind of the end of the story on that scale. Let's now zoom in and see how all of the subunits within that work. So within our own neighborhood, the closest thing to us is Andromeda. That was, of course, the first spectrum. And as we've seen, this galaxy is heading straight for us. So in about 10 billion years or so, Andromeda is going to collide with the Milky Way. And that's going to be a beautiful thing. Now, if you think about it, it will. Because when galaxies collide, you have to remember that galaxies are relentlessly empty. So if you shrink stars down to the size of grains of sand, there's miles and miles of space in between them. So if you imagine your friend a couple miles away with his grain of sand and you're trying to throw one to hit it, it's an unlikely event. So when Andromeda hits the Milky Way, chances are good no two stars in the field will actually collide. So viewed from within, the collision of two galaxies will just appear as a gradual brightening of the stars of the night sky, because there's about twice as many. On the other hand, when you view it from the outside, you get this train wreck. You completely destroy the beautiful spiral pattern, right? Now, if we look even closer at home, let's look at what happens to the fate and future of our own sun and solar system. So here's a Hertzsprung-Russell diagram in schematic form. Right now, the sun lives at point A. So in 3.5 billion years from now, the sun will move from point A to point B, which doesn't look very dramatic on this diagram, but it's kind of important in that this spells the end of life on Earth. Okay, in 3.5 billion years, or even sooner, the sun will be 40% brighter, and that will cause a real global warming where the oceans will boil and the planet will be sterilized. So it might happen sooner, but the longest we have, I won't make any political statements, but in 3.5 billion years we're toast, or shrimp maybe because we'll be boiled. But so is there any hope? Well, I should say, well, as far as the Earth's concerned, Earth doesn't care if we're on the surface or not, so Earth will survive this without any problem. However, in about 7 billion years, the sun will move up to point C when it becomes a red giant. Yesterday we heard about dwarfs and giants. When the sun becomes a red giant, chances are good that Earth itself will be engulfed by the red giant sun, and the planet will cease to exist. So what hope do we have? Well, here's the Earth being swallowed by the red giant sun. The way to avoid that is for a red dwarf to come save the Earth. So there is some probability in the next 3.5 billion years that a wandering star will come close enough to our solar system and eject the Earth, thereby saving it. It will actually make the biosphere live longer. That's a separate story I don't have time to tell. What are the odds of this happening in 3.5 billion years? The odds are 1 part in 10 to the 5. Now, that's not so bad. You might say, well, I don't really want the Earth to be ejected cold and alone out into space. Maybe I want it to be captured by a passing star. There are other scattering interactions that lead to capture. Often they're kind of chaotic and interesting. And of course, they're lower probability. So the odds of Earth being captured by a passing star during the next 3.5 billion years is about 1 in 3 million. That's about the odds of you winning a state lottery, which makes you wonder why people line up to buy lottery tickets. Now, what's interesting about this is, one, these are the odds, but what's interesting, you can actually calculate these odds with a straight face. Because think about what you need to calculate what I just told you. You need to know the density of stars. Well, we know that. We can measure that. We know to know their velocity or velocity distribution as well. We can know that and measure that as well. We also have to know what happens when a passing stellar system interacts with our solar system. We have to know the probability that you'll get a capture or an ejection. You need to know the cross-section for interaction. And the way you do that is you make numerical experiments. The winters are quite long in Michigan, so I've made about 1 million of these. And they're all sitting on my computer desk. And what I can then do is mine all of those results and calculate the cross-section for capture to occur, for ejection to occur, for eccentricity increases to occur. And here are the eccentricity increases and capture for planets around other stars. This kind of work is actually interesting to see how cluster environments shape solar systems that we see today. But that's not the part of our story, but the same physics informs how our own solar system, or how our own set of solar systems in the present day universe evolves to its present form. So we have to move on with our story because, again, we only have 20 minutes. I have 20 minutes left. Now, what happens is that as the star formation proceeds and stellar evolution proceeds, the stellar material in the galaxy goes through this ecological cycle, which is called the karmic cycle of stellar evolution. So molecular clouds make stars, some of the stars lose mass, some of the stars blow up, some of the mass gets locked up into stellar remnants, and around we go. Now, the galaxy will continue to make new stars through conventional star formation processes until it literally runs out of gas. Now, how long it takes to run out of gas is something you have to project. If you just took the current star formation rate today and the current gas content, we would run out of gas in about a Hubble time. But as the gas supply goes down, the star formation rate goes down as well. So you can keep it going for a few more e-foldings. You also get a little bit of recycling, a little bit of extra gas onto the disk, and if you turn all the knobs to one side, you can keep star formation going for about 10 trillion years or so. Of course, the star formation you have in that last decade will be much less than what we have now.
Does all this take into account Andromeda hitting us?
Yeah.
Well, again, Andromeda just gives you twice as many of these events
That
happening.
could double your rates here.
Yeah, but we don't care about factors of 2 when we're talking about factors of 2. Yeah, so let me defer that discussion until the discussion. So anyway, the point is that the galaxy runs out of gas and we run out of conventional star formation in about 10 to 100 trillion years. Well, how long do the actual stars live? Surprisingly, this was not well known, because the smallest stars live for far longer than the current age of the universe. So what we did is we did some stellar evolution calculations of red dwarfs, which are stars with 1/4 to 1/10 to 0.08 times the mass of the sun. And they live, you can do projections and figure out they live for about 1 trillion years on the back of an envelope. But they live even longer than you think. And the reason why they live even longer than you think is that these little stars remain convective for their entire lifetime. So whereas a star like the sun only has access to the central 10% of its mass while it's burning on the main sequence, a small star has access to 99% of its mass. So you get an extra bonus mass. You can burn much more of your mass. And it does it at such a miserly rate that it takes a long time. So there's 2 points I want to make with this. One is that if I zoom in on the inset diagram, you see that the mass, or the lifetime as a function of mass, is measured in trillions of years. So the smallest star with present-day metallicity will live for about 10 trillion years. If you crank up the metallicity like we expect, it will live correspondingly longer. The other thing you notice in this HR diagram is that a quarter solar mass star, as it evolves, is moving up, and it will eventually move up here and become a red giant. Stars that are smaller turn around and get bluer and become blue dwarfs. So I'm down to 5 minutes. This allows us to understand how it is that stars become red giants, but I don't have time to talk about it. But you can propagate that thought through the stellar structure equations and write down on the blackboard why a star becomes a red giant. And this is another thing we learned by studying the future of the universe. So moving on, stars get brighter with time that the big stars die. Those almost compensate so that the Milky Way will have a nearly constant luminosity as a function of time. And that will continue until we come to the end of the stelliferous era. So the point here is that both star formation and stellar evolution end at about cosmological decade 14, when the universe is 10 to 100 trillion years old. Now I'm only through 2 of my 5 eras, and I'm down to 5 minutes, so I'm going to have to speed up. So nuclear physics gives us what happens next. And what happens next is that after all the stars burn out, we're left with degenerate objects. Here, degeneracy does not refer to the moral state of the universe, but rather the quantum mechanical state of matter. So we have brown dwarfs, white dwarfs, neutron stars, and black holes. By number, there's almost equal numbers of brown dwarfs and white dwarfs. By mass, the white dwarfs are about 10 times more massive. So most of the mass of degenerate objects is locked up in the white dwarfs. So I told you the star formation came to an end, but I sort of lied to you. I also told you that stellar collisions were rare, and there I didn't lie. But if you wait long enough, the brown dwarfs will collide. And when they collide, they will make new stars. So if you look at our Milky Way today, there's billions and billions of stars all shining brightly. If you look at the Milky Way of the future, even with the factor of 2 from Andromeda, the number of stars shining through brown dwarf collisions will be 1 or 2. And they will be M dwarfs. They'll have luminosities sort of 1,000 times less than the sun. The white dwarfs will collide sometimes, but usually when they collide, they're not big enough to give you an explosion. They'll just give you a funny white dwarf. But what they do is they will hoover up these dark matter particles, or so we think, and that will endow the white dwarfs with a luminosity source they wouldn't otherwise have. So they will be the brightest objects in the sky, perhaps the most important energy generation mechanism in the future, and they'll each have powers rated in the quadrillions of watts. To put that in perspective, Earth intercepts 100 quadrillions of watts of solar energy. So it's 100 quadrillion watts that runs the entire biosphere of the Earth. And it's a comparable amount of power that each white dwarf will be giving the universe from dark matter annihilation. On even longer timescales, the galaxy will relax. So right now we'll have a messy disk after the Andromeda collision, but then the dynamical relaxation will scatter the stars to the next larger scale structure. And that will happen on a scale of 10 to the 20 years or so. Now this continues until the objects themselves sublimate. We think that the degenerate remnants, mostly white dwarfs here, will decay through proton decay. Now there's many, many channels available, and we haven't actually measured the lifetime yet, but yet this is an experimental science. The proton decay experiments are in the 3rd or 4th generation, depending on how you count. And right now we have an upper limit, or a lower limit, that we know that the proton lives longer than 10 to the 33 years, and there are theoretical reasons to believe it lives for a timescale less than 10 to the 45 years. So we have, except for this factor of 10 to the 12, we know exactly what's going on.
But you went from factor of 2 to 10 to the 12.
Well, there's a factor of 10 to the 12 uncertainty in the proton decay lifetime. So protons decay through various Feynman diagrams, including this one. And their evolution, or the proton decay then drives the evolution of the white dwarfs that look like this in the HR diagram. So they get bigger in radius as they get smaller in mass until they're about the mass and radius of Jupiter. And if you think you start with a carbon-oxygen white dwarf, at this point you'll be just a ball, a Jovian-sized ball of hydrogen ice. And then as that ice continues to decay, it goes away until you have no star left. So that takes us to the end of the degenerate era. So we have brown dwarfs, white dwarfs, neutron stars, black holes. They go through this set of physical processes that I described. So the universe will be very interesting until all the protons decay, and then we're left with what? Well, then we enter into the black hole era. Now remember, black holes are defined to be things that are so dense and gravity is so strong that not even light can escape their surface. So this time in the future of the universe, black holes will be the brightest things in the sky. And here's what we have. Each galaxy has a supermassive black hole in the center with a mass of millions to billions of suns. Each galaxy through supernova will produce around 1 billion stellar mass black holes, although this number is uncertain. And all of these black holes will decay through Hawking radiation. The time scale is about 10 to the 65 years times m in solar units cubed. So the black holes will proceed this way. All the stellar mass black holes will have about 10 stellar or 10 solar masses, so they'll decay in 10 to the 68 years or so. The supermassive black holes will decay in anywhere from 10 to the 83 to 10 to the 90-something years. And even if you took all of the matter in the observable universe today and balled it up and made it into a black hole, that black hole would evaporate in only 10 to the 131 years. So compared to infinity, this is a small number. And what this means is that the black hole era will in fact come to an end. And then we enter into this dark era. In the dark era, as my colleague Laughlin said on TV once, it will be very, very dark. And the reason is that there are no longer any stellar-like bodies left. So if you think about the story of the universe, instead of ashes to ashes, dust to dust, it's really particles to particles. Because at the Big Bang, and for the primordial era, we had no stellar objects. The primordial era ended when we formed the first stars. And then we went through regular stars, degenerate stars, black holes playing the roles of stars, and now we're back to particles. So you might think that the universe is pretty boring here, and you might be right. But there might be a way out. The vacuum energy that we've heard so much about, the dark energy, says that empty space has an energy level associated with it. Well, if you're going to buy the idea that empty space has an energy level associated with it, it's not that much more of a leap to buy the idea it might have two energy levels. And if that's the case, we're living in some false vacuum with a high energy level, which allows for the possibility of a transition to a lower energy level. And whatever's causing this energy level will be some vacuum state of some quantum field. So this quantum field can make a phase transition from high to low. What you get is you get little bubbles of the new phase nucleating in the sea of the old phase. And then the phase transition can come to a completion under the right circumstances. Now, if I put another if on top of this, if that field that's driving the dark energy and it has a phase transition also couples to the mass of the particles or the strength of the forces, then the laws of physics can change during this phase transition, and the universe can get a new start. So if all of those things happen, we can restart the universe. Now, at this stage in the story, as you might guess, things are beginning to get a little bit speculative. So let me summarize and let me end. What I'd like to say is that our current understanding of the laws of physics and the current state of the universe lets us make a working picture of the future. I'd like to argue that studying the future gives us insight into current astrophysics. We can understand why stars turn into red giants. We can understand the mass of dark matter halos. There's also some dynamics that we learned that I haven't had time to talk about. And since people will ask me, there are two disclaimers that one needs to put on. As you go further and further into future time, quite frankly, you know less and less about what you're talking about, right? So I chose to cut off this projection at 10 to the 100 years.
I hope you'll start soon.
What's that?
I hope you'll start soon.
Oh. But the same thing happens when we talk about the Big Bang, if you think about it. When we go from the present day back into the past, in the immediate past, you guys have redshifts of things, and you know exactly what we're doing pretty well. When we go past the micro background epoch at 300,000 years, we still know pretty much what we're doing. When we go back to when the universe was 1 second old, when Big Bang nucleosynthesis was happening, we still have a good understanding of nuclear physics. But the further you go back from that, again, the less and less we really know. And it works in both directions, in different ways. And finally, I've assumed that we actually know what the laws of physics are. If the laws of physics are more complicated, if there's time variations, if there are new forces, those changes will make changes in the projection I presented here, both large and small. So, thank you.
Now you have seen the difference between astronomy and astrology. What he told us that will happen. Okay, I was missing one strain. How long will our culture go along? So you would have to, and an important feature of our culture is that we can enjoy a good glass of Burgundy or claret. You should have said parallel, how long that will work.
No, that would be nice. The one thing I'd like to emphasize, because
No. Now we have questions.
Oh, I would like to make one quick point, and that is that people might ask, well, what about life? Why did I not talk about life? And there's a big difference between talking about a projection of the future of the physical universe and anything about life or wine. And that is that for the physical universe, when we talk about stars, we have equations. We have the equations of stellar structure, and we even think they're pretty good. So even someone like me can do the calculation and give you the result with some confidence. As soon as we go from the physical universe to the biological universe, we know much less, and projections we know much less.
I just want to apologize for all of us, but your talk begs for heckling.
Oh.
Okay.
And just another disclaimer, I mean, it's a wonderful talk, Fred, but first of all, I would use the title A Possible History of the Cosmos, not the future history of cosmic expansion. And that's because you made an assumption, acknowledged but not justified at all, which is that dark energy is constant. I think until we have a picture, a physical picture of what dark energy is, we have no idea. It could change sign tomorrow. We really don't understand. And just on that point, because it's important though, I don't have to say, I don't even like the term, and I'm nervous of saying it here, I don't like the term expanding universe even. It's expanding now, and as far as we can tell, it's been expanding up to now. But evolving universe is what we live in, and I always think that's the difference even between Friedman and Nathan. The general thing is an evolving universe. We have, there are many, many possibilities for the future, and until we have a picture of dark energy, it's pretty much wide open. I really hope.
Well, let me add one thing to it. I mean, fair enough that we don't know what dark energy is doing, and the particular movie and the isolation and the island universe part of the story is predicated on the fact that the dark energy will continue to exist for a couple Hubble times. After that, it won't matter. But the other thing I'd like to emphasize is that most of what I talked about and most of the actual calculation that went into this class of projections is not just saying what happens to the future expansion, but what happens to the future of galaxies, what happens to the future of stars, what happens to the future of black holes. As long as the universe lives for long enough for that timeline to play out, all of the physical processes, except for perhaps the isolation, will happen. So the big question is, will the dark energy evolve in such a way as to lead to immediate, or on these timescales, immediate recollapse? Now, it could happen, never say never, but we have to understand that there's never been any evidence that the universe is closed and will recollapse.
Okay.
The error bars have always been big enough we can allow that, but they've always been pointing more towards an open universe. Perhaps some of them
We had three speakers in this session. I would like to know the opinion of the other two fellows in this
Let me
session.
say that I agree with the comment about, but let me say that I think there's a real prospect in the next 15 years.
Can you understand him?
No.
Okay, I think there's a real prospect in the next 15 years of at least determining whether the dark energy is a constant or changing.
Yes.
So that would at least address a very critical question of whether your assumptions about the future are even approximate.
But right now, if you believe the current error bars that W is -1 plus or minus 0.1, or even 0.1, nothing I did here will change except for the exact number.
But you're going a long way in the future. I think it's clear that if dark energy is not a cosmological constant, it's close enough to one of, let's say, another 10 or 20 or 30 Hubble times, we may as well assume it is. But beyond that, we don't know enough.
Right, but the point is that at that time, each thing will be each bound structure will be isolated, that it won't matter very much what the background is doing.
No, I agree. Once it gets beyond the horizon,
right.
What happens after that, who cares?
Unless it comes to a screeching halt and recollapses for some reason, then it will matter.
Yeah,
It's less than -1.
but that's the point. But we know that if it's going to recollapse or go to a big rip, the timescale for that is probably 100 times the current age of the universe. So we can go to we can talk about a trillion years. We can't talk about we can't talk about 100 trillion years.
I would say one thing that
Put your head in bed for 100 trillion.
Sorry, I can't hear you.
one thing that I don't believe you've given any treatment to is we really don't understand the structure of time itself. You can read my poster if you want on that. That takes out the dark energy.
Yeah, well, on the issue of time, one has to assume that standard GR is the story, and there's nothing pathological happening with time. That is an assumption that's embedded in my last disclaimer here.
Just another very quick disclaimer. You talked about proton decay as one of the things that would happen in the very far future, but of course there is yet no empirical evidence that protons decay. Nobody's seen a proton.
Right, we only have a limit so far, yes.
So that's a bit speculative.
No, well, it is speculative, but there is an argument, namely that if there's really only two choices. Either there's baryon number conservation or there's not. Agreed? Well, if you look around the room, we're all baryons. If you look around the universe, we're all baryons. So apparently, some process in the early universe broke the baryon-antibaryon asymmetry and gave us baryons. That process of baryogenesis is weak. It only gives us in the early universe one extra quark, or one extra quark for every 30 million quarks and antiquarks. But if that process violates baryon number, then the protons will decay because there's a proton, there's a lower energy state available to it, namely a positron. The only thing that would prevent it getting from the high energy state to the low energy state eventually is if there's a law that forbids it. But it's unlikely, not guaranteed, but unlikely there's a law that forbids it, namely because you're here. Right? So we have observational evidence in spades that suggests somehow baryon number is violated. Now, that's not an airtight argument, but it's a pretty strong argument that something will happen. Agreed, we need more experiments.
Just a comment on the issue of the future observability of cosmic expansion, say in 10 to 11 years. So R.B. Lowe had an interesting paper last year saying that you should still be able to observe the expansion from stars ejected from the Milky Way. Hypervelocity stars will trace the expansion and you can still observe that.
Yes, that's a good point. Although there's not a lot of them, so you have to have just right conditions to do that.
You
So.
can put a very big telescope in 11 years.
Yeah. But you do it a lot of times.
Okay.
It wouldn't cost much per year.
I think we all deserve coffee. You have to.
I don't have a question. I have, if you're done with questions, I just wanted to let people know, if you had asked for that, the letters between the last two letters from 1953, because I don't see you right between Schleifer and Hubble, where Hubble talks about Schleifer taking the first steps and gives him credit, basically. I have about, I think, 4 or 5 copies here. If you would like a color copy to frame and put in your office to fake people out that you have the originals, I'm happy to do that too for you. But these are black and white copies, and if you'd like them, they're back here.
Okay. Could I just mention something in the same thing? Just for anyone who enjoyed this talk, I can't resist, I don't need to embarrass you, Chris, but Chris Impey has written a lovely book on this subject called How It Ends, and I reviewed it about a year ago, and I'd highly recommend it if anyone enjoyed this. It's exactly the same topic.
Well, he also has a book on this topic.
Sorry.
That's why he was invited.
Where are we going wrong? We should be happy.
No, I think we all deserve the coffee.
Yes, you all get the coffee.